Hello viewers, welcome to my class of design of steel structures. I am Dr. R.P. Singh Kushwaha, a structural designer and chartered engineer. I am professor in civil engineering department of Global Institute of Technology, Jaipur. Today we are going to design a plate girder bridge. So kindly see the video carefully and get benefited. Thank you. Of plate girder bridge for railways. So first of all, we have to understand the drawings. What is plate girder bridge? So you can see in these pictures, these two, one, and this is another. These two are plate girders, and these plate girders can be seen here. This is plate girder at the span of this bridge. So this is plate girder, and above this plate girder, these squares are seen here. These squares are 1, 2, 3, 4, 5. These squares are railway sleepers. As you can see in this picture, this is railway sleeper. And the same way, you can see here, these are sleepers 1, 2, 3, 4. These are railway sleepers. And these are railway lines, main railway line, the one, and this is another. These are known as stock rails. And inside, you are seeing here another set of rails, one this and another this. These are the guard rails. These are just for safeguard of the wheels. The wheels should not derail at the bridge side. So uh, along with these, there are some fixtures which are fixing the rails on the sleepers, and hence the combined track is in functioning. So we have to look at some steps which will be used in designing of the plate girder bridge for railways. So first of all, we have to see the standard loadings for railway bridges. So first we will take dead load. So dead load of the stock rail, and second is the weight of guardrail, and third is weight of fastening, and fourth is weight of sleeper, then salvage of the broad gauge main line. So this will be a total of the, this total will be dead load. Now come to the live load. So we have to take live load according to IRC bridge rule, page number 2122, and we will take the live load from there. And third, we will take the impact loading. And impact loading, we have to find out first of all the impact factor. As you can see, this is the formula for finding out the impact factor. So we will find out the impact factor by this formula, 0.15 plus 8 divided by 6 plus L. So by this we can factor our bending moment and shear force, which is acting for live load. So now come to the design of the plate girder bridge. As here you are given a problem to design a plate girder bridge for a span of 20 meter as shown here on a broad gauge line. Means you have told the gauge of the railway line and the span of the bridge 20 meter. So first of all, find out the dead loads. So weight of one guardrail is 280 Newton per meter, and weight of one stock rail, that is 260 Newton per meter. Weight of fastenings per meter, it comes out to be 300 by 2 equal to 150 Newton per meter, because it is 300 is for both lines. So now for RCC sleeper, the density of the sleeper is taken 1.4 numbers of sleepers per meter length, and the weight of sleeper is 3660 Newton. So half weight of sleeper uh, per meter length we have to find out. So half weight of the sleeper is 1830 Newton. So weight of sleeper per meter length will be 1830 multiplied by 1.4. This is sleeper density. So it comes out to be 2562 Newton, which is number 4. Now for finding out the total DL, we have to add 1, 2, 3 and 4 heads. So this comes out to be 3252 Newton per meter. Now self weight of the plate girder, we have to assume it 0.79 multiplied by the L. L is the span of the bridge, effective span. So it comes out to be 15.8 kilonewton per meter, or you can say 15,800 Newton per meter. So now the total dead load on the plate girder comes out to be, on addition of these both two, it comes out to be 19,052 Newton per meter, or you can say 19.05 kilonewton per meter. Now find out the live load by IRC bridge rule. Suppose this is 95 kilonewton meter, because presently we are assuming it 95 kilonewton per meter. So live load for shear force, it comes out to be 1251.5 kilonewton. These both are to be taken from the IRC bridge rule. So now the impact factor comes out to be, putting the values here, 0.15 plus L, 8 divided by 6 plus L span of the bridge. So it on solution comes out to be 0.457. Now finding out the maximum bending moment. The maximum bending moment due to dead load, it comes out to be 952.5 kilonewton meter as shown here, and due to live load, the total maximum bending moment comes out to be 4750 kilonewton meter. Due to impact factor, you may multiply this uh, bending moment by the impact factor, so it comes out to be 2170.75 kilonewton meter. Now the total bending moment, add all the three heads 1, 2 and 3, so it comes out to be 7873.25 kilonewton meter. Now find out the maximum shear force. So first of all, maximum shear force due to dead load, you may find out it 19.05 into 20 divided by 2, it comes out to be 190.5 kilonewton. And for live load, it comes out to be, because it is for the both rails, so the one both supports, so it comes out to be 1251.5 divided by 2, it comes out to be 626 kilonewton. And now due to impact load, so multiplying by the impact factor, so 0.457 multiplied by 626, it comes out to be 286 kilonewton. And now total shear force comes out to be, on addition of all these three, 1102.50 kilonewton. So now design of central section of PG. As we all know, design depth of the web D is equal to 1.1 under the root m divided by sigma b into TW, thickness of the web. So here sigma b is a level bending stress, which is equal to 0.66 Fy, and it comes out to be 165 MPa. And assume the thickness of web TW this TW to be 20 mm. So depth of the web DW is equal to 1.1 under the root 7873.25 into 10 raised to power 6. The maximum bending moment in Newton mm and divided by sigma BC into 20. So it comes out on solution, it comes out to be 1699.07 meter. You may say or assume 1700 mm, or you can say 1.7 meter. So now check for thickness of web TW for the shear. So the total shear force divided by sigma B into TW, this, where sigma B is equal to 0.4 Fy. So it is prescribed by the IS code. So the total thickness of web comes out on solution is equal to 6.485, which is less than our provided 20 mm thickness, and it's okay. Now design of flange. If you want to improve it or you revise it, you may revise it, or you may reduce the thickness of the web, but it's okay. So design of flange. So area of flange should be equal to m divided by sigma b into DW, depth of web, and sigma b here again 0.66 Fy. So area of flange is BF into TF, width of flange multiplied by the thickness of the flange. But again, assume the thickness of flange to be 20 mm. So on putting the values and resolving, the BF comes out to be 1443 mm. Say you may assume it as 1450 mm. Now you have to check it for maximum tensile stress. So sigma BT should be equal to m divided by I into y max. This is the binding equation. As you all know, by binding equation we are checking it, the maximum binding tensile stress. Here the IXX is, as you can see here, it comes out to be 5.108 into 10 raised to power 10 mm4, and Y max comes out to be 870 mm, because as you can see here in this figure, the half of this portion plus 20, so it comes out to be 870. Hence putting the values in the equation, so sigma BT comes out to be 134.08 MPa, and the permissible is 165, hence it's okay. So now come for check for shear stress. So shear stress tau should be equal to maximum shear force divided by area of the web. So maximum shear force is 1102.15 to 10 raised to power 3 divided by area of web 1700 into thickness of web 20. So it comes out to be 32.42. While the allowable stress is 0.4 Fy, and it is 100 MPa, so it is far less than 100 MPa. Hence the design is okay by point of view of the shear. Now design of weld. So now we have to design of the welded joint of the flange plate to web. So total load on the weld, it comes out to be total shear force multiplied by the area of the web into maximum fiber distance y max divided by Ixx. So it comes out to be 5544.56 kilonewton, and strength, because the welded joint will be on both sides of the flanges, so the strength is 2 times Ks into Lw into tau, and the total force on equating total force, the size of weld comes out to be 0.19 mm, but already we are providing 5 mm thickness of minimum size of weld, hence it's okay. Now we have to go for the curtailment of the flange plates. For curtailment of flange plates, we will go into the next video lecture. So thank you for attending the class. Thank you very much.